Hi, everyone. Um, I just wanted to get back on here. I think it's been a few weeks since we've done a presentation here. So sorry about that. I wanted to get back on here. Sorry. Let me just make sure nothing intrudes on us. Okay. And continue our training, which was on effective connectivity in clinical practice, I believe was the title. Last time we did part one, this will be part two, and we're just going to keep kind of going through this series to cover this information as best we can. So if you remember, we started talking about the idea of measuring effective versus functional connectivity. I actually just had a meeting with a woman this week in London where we talked about this concept, and that is measuring functional connectivity with EEG data between pairs of electrodes is a highly error-ridden technique that research has now shown. I'm sorry. Oh my. There we go. Sorry about that. The research has now shown will show valid findings, but it will also show invalid, spurious findings at about a 50-50 clip, depending on the case. So you're left really not being able to know which one is a true finding that you should train with neurofeedback or any other type of neuromodulation. So moving towards this effective connectivity model where we use causality and a multivariate autoregressive statistical strategy gives you much more accurate assessment, and we've shown more effective intervention when you do that. So what we want to do is go through some information, including series of clinical cases, looking at typical QEEG procedures, including bivariate coherence analyses, comparing them to multivariate coherence procedures based on first principle components analysis at the surface, and now a more improved metric, independent components analysis at the dipole level, at the source level, using Grainger causality as a causal model to look at this data and information. So this technique we're going to talk about uses something called independent components analysis. And within the neuroscientific community, there's no debate about the validity of this technique. It's been published in some of the greatest and most eminent journals in the field, and it's used at some of the highest notch universities, medical centers, and neuroscience centers in the country and the world, for that matter. The original publication looking at ICA was first produced by Scott McCaig and colleagues in 1996, and it compared channels of EEG to the ICA procedure where you get components that includes data across multiple channels. So it's a much more comprehensive way to look at the data, and a much better way to artifact and get cleaner data as well. And as we have found, a much better way to get more precise, accurate, and source localizable findings as well. So here's another publication. This was in Journal of Neuroscience Methods in 2004, where basically that explains what the ICA toolbox does in EEG Lab, which is the premier software for producing this type of information. And you go from the scalp EEG to what are called ICA sources, and then to scalp projections. So the scalp projections are just basically a topographical map of each of the component sources, which are different aspects of the EEG across multiple channels simultaneously seen. And once you have that, you can decide which ones are artifact and which ones are not artifact For example, this one is obviously an eye movement or eye blink. This is clearly muscle activity in the right temporal region. Same here. And then you can see on the left side the same thing there. So artifact is very easy to detect in this way. You just remove it and you're left with only the prominent EEG activity over different components or sources. So the flow of analysis goes from the EEG data collection, depending on how many channels you utilize. Most people in the neurofeedback field collect QEEGs with 19 channels. We are now a proponent of going up to 32 channels at least to get more precise information. You then process through an independent components analysis to get your sources and topographical maps. From those typographical maps, you go to a dipole source localization. So it tells you where deeper in the brain that activity is coming from. Then to a procedure called multivariate Grainger causality, which is a multivariate autoregressive technique that tells you the causal relationship between what happens at one source or dipole or one source localization or dipole to another source localization or dipole. And you can actually measure that directionally and in a reciprocal fashion as well, which blows up the idea of measuring connectivity and the type of information you can get from this. And then lastly, to what are called graph theory metrics, where we can get summative metrics of all connectivity within given networks and measure the efficiency of those networks over time. So Grainger causality as a statistical technique is not new. It was created in 1969, and it has the following equation that you can see there. The simplest way to think about this is it is a form of multiple regression where what happens in one data set is used to predict what happens in another data set. Okay? And you can do this with any number of data points. So we can do it for 2, 3, 4. I don't recommend it with 2. We can do it with 3, 4, 5, 6 data channels of EEG and their source localization, dipole localization. Or you can do it with 32, 64, 128. The number is not limited in any way by the equation. So it basically gives you a causal metric to interpret your data, factoring in all of the multiple inputs that are happening simultaneously in that person's brain based on their sources and source localizations or dipoles. Okay. And it is a MVAR statistic, what we call a multivariate autoregressive technique. And we've kind of described that process a little bit here. If you have questions about that, feel free to ask them in the chat. So what happens when we actually apply this technique? We see up top an EEG that has artifact built into it. We do the independent components analysis. I think this is a 32-channel EEG. And we remove artifact, and then we can see at the bottom a cleaned up EEG. And it works really, really well. And not only does it work really well and you get very clean data, but you get to keep the majority of your data. So we're recommending that, for example, an eyes closed EEG be recorded for 10 minutes. In the typical scenario where you do manual artifacting and you remove all of the data, if there's artifact in one section of the data, you're fortunate to wind up with 60 to 120 seconds of data that you then compare to a normative database. Well, with that limited amount of data, you can't really see changes over time in that data. So what the typical QEEG does is it averages over that time period and takes the average compared to the average of the database. Well, there are problems with that. Let's say, for example, that you've got 50 microvolts of alpha for half your EEG and 5 microvolts of alpha for the other half. it's going to show up on the average being at around 27 microvolts. And when you compare that to a database, that may be normal or only mildly elevated. But we know that that person emits 50 microvolts of alpha at certain time periods. Well, we're losing that data by averaging it, and we want to know about that happening in that person's brain. So there's a cost to that. In the ICA procedure, you get rid of the artifact and you keep the rest of the EEG. So out of 10 minutes of data, it's very typical to keep 8 minutes of data, and we can look at ebbs and flows and changes over time as well, and changes over time in connectivity, which can be very important. So from that data, we have, for example, 8 independent components. You can notice those on the top 2 rows here, and they're numbered from 1 to 8. So each component, you'll notice, has a very different map. So what it does is it statistically pulls apart components that are showing different type of EEG processing. Again, across all channels, but different foci. So for example, the first one shows us a peak over the left temporal parietal region, whereas the third one shows us a peak over the right temporal parietal region. Again, if we were averaging these out, we might not see very much, but this teases apart different activity in that person's brain that is happening over and over again, that is important for their functioning. So we get to see much more fine-grained detail, and then later in the stream, we're going to get to source localize that fine-grained detail. We can also look at this on a spectral plot after we've done the ICA, and we can determine at certain frequencies, what are the most important uh, areas of activity. So here you'd see at 10 hertz, which was picked in this slide, that the most important component is over the left temporal region in their alpha activity. Well, that's interesting. So then we go back here and we say, oh, so this is alpha. That's what happens when they emit alpha and over the left temporal region. Well, that might have a significant clinical impact for their presentation, whereas some of these other frequencies might have other components that are more important. So we can really tease apart and isolate data and functioning in a much more detailed way. We then look at the component properties of each one. It's a little hard to make out, but here you can actually determine what percentage of the variance is explained by that EEG, by that component of the EEG, that source. So this makes it really fascinating. So remember I said they're numbered from 1 to 8. So they're rank ordered. So number 1 explains the greatest percentage of variance in that EEG, and then it goes down from there. So we might determine, well, 1 and 2 are really important, but 7 and 8 are not. So we can begin to isolate areas that are important and see certain components relate to certain types of EEG activity more than others, and try to relate that to their presenting symptoms and issues, as well as we try to understand their brain activity. And here are the dipoles of those sources, or the source localizations. Again, the numerical system follows, so we can see the area, the activity at the first IC, or independent component, which was over the left temporal parietal region, actually source localizes to the left posterior frontal region of the brain. And we get to see all the dipoles in place in 3-dimensional view. And you can also get the XYZ Talairac coordinates of those, which will give you the exact localization within the brain within about 3 to 5 millimeters. So it gives you very precise, detailed information. From there, we take those dipoles, we run the Grainger causality procedure, and now this shows us our connectivity across these regions. We'll get into this in more detail, but for this, I just want to explain that there's 6 planes you see. You can't really make it out here, but these are done over time. So if we have 8 minutes of data, we're going to do one of these about every 1.5 minutes or 90 seconds. and you can see how they change. See how the colors change over time? That's the connectivity changing over the course of that EEG. So you get lots of information about that. And then we get information here of what we call reciprocal causality. And again, we'll talk more about this in individual cases. But reciprocal causality, where now we have arrows pointing in certain directions. So we take the causal value, let's say from 1 to 2, and we take the causal value from 2 to 1, and we subtract them. The one with the lower value, or where it's going in a negative direction, shows the lowest causal connectivity directionally. So we have an arrow pointing to that location. In this scenario, for this patient, we see arrows pointing towards the dipoles in the front of the brain, which tells us that those are weaker locations in the connectivity train of data flow. And that gives us an idea of areas that are more important to include in our training and treatment of that patient as well. So this is information you cannot get out of functional connectivity or paired coherences in any way, because it's just a correlation. Okay. Whew. Sorry about all that, but there was a lot of background to cover to understand all of this. We're already at about 17 minutes, so we're going to have to cut this off again. And then next time when we resume, hopefully next week, I'll try to do this every week as best I can. We'll deal with our first case, which is a case on the autism spectrum, and we have several cases to go through and talk about what this data looks like. All right, again, if you have any questions, feel free to post them in the Facebook group. You can even do like a little live yourself where you show yourself asking a question on video, or you can just post it otherwise. And then it'd be great to have dialogue back and forth between people and invite other colleagues. And we want this information to be as available as it can be to the greatest number of people. All right. Well, thank you all for listening, and hope you have a great weekend and week, and hope to resume again next week. All right. Have a good day. Bye-bye.